In this video, we're going to take a look at the empirical formula, which is the simplest whole number ratio of atoms in a compound. So before we dive into the empirical formula, it's important first that we understand what the term ratio means. So you should remember from about first year maths what to find a ratio means. So if I want to find the ratio of pink to blue here, I have 1, 2, 3, 4, 5 pink. And it is to 1, 2, 3 blue. So 5 is to 3 is the ratio. I could use that ratio then to start calculating percentages. I can use it to work out how to make different things from it. It's the simplest whole number ratio, but from there we can do a lot of work with it. The pink to blue of this one, well, if I do pink first, I've got 1, 2, 3 pink, so 3 pink is to 1, 2, 3, 4 blue. The next one, similar concept, looking at carbon is to hydrogen. So if I look in my compound here, I've got 2 carbons, 5 hydrogens, so carbon to hydrogen is 2 is to 5. Now in the next one, I've got carbon to hydrogen again, and I've got 2 is to 6. Now, what the flag here for me is, or what the kind of thing that makes alarms go off in my head, is that 2 is to 6, while it is a correct ratio, it's not the simplest ratio. So another way that I could write 2 is to 6 is I could divide both of those by 2, and I could end up with 1 is to 3. And that would be the simplest whole number ratio of carbons to hydrogens. I'm then going to look again at carbons to hydrogens. In this case, it looks like 2 is to 5. However, I must make sure I go back and I include this hydrogen here as well. So again, this one is 2 carbons and I've got 6 hydrogens, so the ratio of those is 1 is to 3. So that's a quick recap of what ratios are and how they work. Let's now look at how they might be included in a chemistry question. So remember, the empirical formula is that idea of ratio. So it's an idea of how many of this versus this do we have. So it says find the empirical formula of a compound containing 40% sulfur and 60% oxygen by mass. So 40% sulfur, right, it says it's that percentage by mass. So actually what that means is that we have 40 grams of sulfur for every 100 grams that I have. So that's what 40% means, 40 per 100. I then have oxygen, which is 60 grams per 100 grams. Now that is the amount of each that I have in terms of their mass, but the empirical formula requires me to have the ratio of the atoms to each other. Now it would be a lot of work to go around counting how many atoms of each that we have, so we do have kind of a shortcut of counting atoms, and that's where the idea of the mole comes into it. So the mole is what I need to find out. How many moles of sulfur are there? How many moles of oxygen? And if I can compare those moles to each other, then I will have a comparison of the atoms to each other, because moles is just the kind of collection of 6.0 times 6.022 times 10 to the 23 atoms. That's how many atoms we have in one mole. So the ratio of the moles translates pretty easily to the ratio of the atoms. So what I'm going to have here is I'm going to have to find out how many moles of sulfur do I have. Well, I've got 40 grams and I want to change it into moles, so you have to go back and do the work here on converting grams to moles and vice versa. We use molar mass, and what we're going to do is we're going to divide by the molar mass. Now the molar mass of sulfur is 32, so I'm going to divide by 32 grams per mole. And remember, when you divide by a fraction, what you're actually doing is multiplying by the reciprocal, so this is what we actually have. And if I tidy that out then for myself, what am I going to have? So 40 times 1 all over 32 gives me 5 all over 4, or I can write that as 1.25. I'm going to do the exact same thing on this side, but instead of using the molar mass of 32, I'm going to be using a molar mass of 16. So it's 60 divided by 16 grams per mole, and then dividing by a fraction means multiply by the reciprocal. So I'm going to have 1 mole over 16 grams. If I do that out in my calculator then, what I'm going to get out is, I'm going to get 3.75. Now, what I need to do to find the ratios of them to each other is you can start to align them as a ratio as they are. So 1.25 is to 3.75, but it has to be the simplest whole number ratio. So I'm going to check what can I do here to get them simplified. Well, what I'm going to do is I'm going to divide both sides by 1.25, and that will make this 1, and hopefully it'll get this to a whole number as well. So 3.75 divided by 125, it does. If I divide both sides by 1.25, the smaller number, that gives me 1 on this side. So I divide it by 1.25, and on this side I do the same. I divide by 1.25. So it's just ratio. So that's the simplest whole number ratio. How do I get the empirical formula then? Well, it's sulfur is to oxygen. And what I've just found out is that it is 1 sulfur for every 3 oxygen that I have. So it's SO3 is what we're looking at. Let's take a look at another calculation. So, when hydrogen gas was passed over 1.59 grams of copper oxide, 1.27 grams of metallic copper was produced. Find by calculation the empirical formula of the copper oxide. So we basically started with copper oxide, we passed hydrogen gas over it, and then we extracted out 1.27 grams of pure metallic copper. So what I'm going to do first is find out how many moles of copper there are in that. So of my CuO, or the copper oxide, just the CuO for the moment, we'll figure out what the ratio of them is now. Of that, 1.27 grams of it was copper. Now remember, the empirical formula deals with the ratio, the simplest whole number ratio of the atoms to each other. So we're going to need to divide this number, 1.27 grams, by the molar mass of copper, which is 64. So I'm going to divide that by 64 grams per mole. Okay, and if you need to see why it's divide, go back to the last part of the video or go back to the molar mass calculation. So you divide that by 64 grams per mole. So 1.27 divided by 64. And what I'm going to get there is how many moles I have, which is not a very nice number. I'm just going to leave it as a fraction for the minute. We can come back and work with it in a moment's time. So that's what I have in terms of the number of moles that I have. Okay, which roughly works out to be 0.0198437.5. Now, to get the oxygen moles, I first need to know the mass of oxygen that would have come out of that. Well, if I started out with 1.59 grams and I managed to extract out of that 1.27 grams of copper, the remaining amount of mass is actually going to be our oxygen. So I'm going to subtract that, and what I get is 0.32. And that's how many grams of the oxygen we have. I'm now going to convert that into moles by taking my grams and dividing by my molar mass, which is 16 grams per mole for oxygen. If I do that, I'm going to get a value of 0.02. And if I put these up against each other again to get my ratio, so remember 127 over 6,400 worked out to be 0.01984 is to 0.02. Well, if you have a look, this rounded to 1 decimal place, or sorry, 2 decimal places, one significant figure is 0.02, and it's 0.02 is to 0.02. Well, what's the ratio of them? It's 1 is to 1 if you simplify that. So you can divide both sides here by 0.02, and it's 1 is to 1. Let's take a look at one more question then. So the next question. The next question is, epoxy ethane is used to manufacture car antifreeze. It is composed of 54.5% carbon, 9.1% hydrogen and 36.4% oxygen by mass. Find the empirical formula of epoxy ethane. So if it's by mass, remember, we just say it's 54 grams per 100. And then to change that into grams per mole, we're going to divide by the molar mass. So we divide by the molar mass of carbon, which is 12. And if we do that, I'm going to have 54.5 divided by 12 grams per mole. I'm going to get 5.54. 16. Let's look at the hydrogen. So 9.1% means 9.1 per 100. To get it into the number of moles, I'm going to divide by the molar mass, which is 1 gram per mole, and then I get 9.1. In the last one then for oxygen, we had 36.4%, which is per 100. To get that into moles then, I need to take my mass and divide by the molar mass of oxygen, which is 16 grams per mole. If I do that out then, 36.4 divided by 16, that's going to give me 2.275. Now, in this scenario, a little bit harder than the other two, we were asked to do it for 3 elements, the ratio of the 3 elements to each other. So you're just going to compare these 3 numbers. The easiest way and the simplest way of getting them all into whole numbers is to take the smallest number that you have and divide that into each of them, because then straight away what that turns this into is 1. Okay, so take the smallest number and divide it into each of the others, including itself, because it turns this into 1. Nice and easy. Then if I do 9.1 divided by it, 2.275, I'm going to get 4. And if I get my number here, 4.54 divided by 2.275, I'm going to get 2 as my answer. So 2 is to 4 is to 1. These listed together as the simplest whole number ratio of each of the atoms together. How do I put that together into the empirical formula? So we listed carbon, hydrogen, oxygen as it was provided in the list, and then it's 2 carbons is to 4 hydrogens is to 1 oxygen. We'll do one more, and I mean one more, and this is the last one this time. So if we take a look, it says when copper reacts with chlorine gas, 6.725 grams of copper chloride is formed. So when we had this many grams of copper to begin with, all of that then gets converted into copper chloride, but when it forms copper chloride, obviously the chlorine gas gets added on, and the mass of that is what's increased the mass of it here. So the first thing I'm going to do, like 99% of your chemistry questions really, is when you get grams converted into moles. So let's convert 3.175 grams into moles. Remember, we've done enough of them now at this stage to know you divide by the molar mass. So the molar mass of copper we got earlier on is 64 grams per mole. And if we pop that into the calculator, 3.175 divided by 64, we're going to get that's equal to 0.0496. That keeps going. Okay, so if we wanted to, we could keep it in the calculator as 127256. So that's how many moles of copper there are. Now I need to find the number of moles of chlorine. Well, to do that, I first need to know out of the total mass, which is 6.725, how much of that's going to be chlorine. So I'm going to take away the copper, because I know the copper mass, and I'm going to take that away, and that will leave me with then the mass of the chlorine. So 6.725, take away 3.175, and if we do that, we get 3.55. So that's how many grams of chlorine there are. And what I would like to know now is how many moles of chlorine there are. So I'm going to have 3.55 grams divided by the molar mass then of my chlorine, which is going to be 35.5 grams per mole. And if I do that, so 3.55 divided by 35.5, if I do that, I get 0.1. So what I'm comparing here in terms of the ratios is I'm comparing, if I round this, I'm going to have 0.05. I have 0.05 is to 0.1. Divide both sides by 0.05, it turns this into 1 and it turns this into 2. So my empirical formula here for copper chloride is going to be Cu, one of those, and then Cl, two of those. And that's it. It is just kind of going back to first year maths, and it is just about taking your time with the calculations. It does all make sense. It is all intuitive. You have seen it before. It is all just ratios. Just take your time with it.